Hello, everybody, and welcome to Inspiration Exchange after our break for the last few months. And I'm delighted to welcome you to what is now our 30th Inspiration Exchange session. For those of you who don't know me, my name is Fergus Imrie, and I'm a postdoc in the Schaar Lab and host these Inspiration Exchange sessions alongside our other organizers, Tennyson Liu and Mihaela. And the subject of today's Inspiration Exchange session is going to be on data-centric AI. Before we get into the session, I wanted to highlight that our lab is now recruiting for PhD positions starting next year in 2024. And I think there's a whole lot our lab can offer you. I'm not going to spell out everything right now, but in particular, I wanted to highlight that we're hosting an open day on the 14th of November at 4 o'clock UK time that you can sign up for via the link shown on the slide. And this will give you an opportunity to meet with some more students from our lab and discuss some opportunities with us and hear more about what we do. So without further ado, I want us to move on to today's session. And today's session will be split into two parts. In the first half, we're going to have three speakers from our lab. First up, Professor Mihaela is going to give a brief introduction and overview of today's session. Then Nabeel, one of the PhD students from our lab, is going to speak about data-centric AI and also hardness characterization methods. And then finally, Rob Davis, one of the research software engineers within the lab, is going to present a data-centric software toolkit. Then in the second half of the session, we're going to move to a roundtable and Q&A session with our three fabulous guests who I'll introduce more formally later in the session. Without any further ado, over to you, Mihaela.
A warm welcome, everyone, to our 30th Inspiration Exchange. It is our third year in a row that we have when we run this exchange. And we started it with the previous generation of students in the pandemic as a way to reach out to others and connect to others while the pandemic was ongoing. And what you see is actually that we have grown this grassroots effort to a continuous sessions. And now you see even here at the bottom of the screen, previous generation students being part of the discussions. So I'm really delighted that we are able to continue that. And thank you very much for joining us and being part of this community and helping us grow it. What we plan to do at the beginning of this academic year is to really have a series of sessions dedicated to reality-centric AI. I would like to introduce in a few words, what do I mean by reality-centric AI and why I and the lab feel that this is a very important focus area for researchers. We have had in the last couple of years tremendous advances in AI, as you very well know, from robotics to ChatGPT. And yet, we have not yet seen a transformation of our healthcare systems, whether it is the NHS system that suffers from severe congestion and staff shortages, or the United States system that has exorbitant costs associated with healthcare. Also, AI has not yet played a big role in alleviating traffic or solving the energy crisis or preventing climate catastrophes, or why not prevent the next financial crisis. And I often like to give this example from education because my main passion is educating brilliant students. I often envision a Roman schoolmaster entering our classrooms today, and I think that they would not be very surprised about what they would see in our classrooms. Not that much has changed in 2000 years. And I strongly believe that we are not just a few breakthroughs away from making really a transformation of these different domains. And in order to be able to do that, we really need a little bit of a different thinking. We need a different AI and machine learning paradigm. And indeed, over the past 20 years that I have been a professor, together with generation of students, we try to engage with these complexities of the real world. We have worked on everything from smart grids and energy to transportation, from smart cities to finance, from network systems to economics. And in the last 7-8 years in medicine and healthcare and education. And it is truly my belief that solving this type of complex human-centric problems is our biggest task as AI researchers. But for that, as I mentioned, I do believe that we need a different way of thinking about AI. And I'm calling this the reality-centric AI agenda, which we believe needs to reorient AI towards these complexities, messiness of the real world. We have put online a manifesto paper that we call the Case for Reality-Centric AI that I would like to invite you all to take a look, read, and come back to us with your feedback and thoughts. And I'm just going to motivate very briefly here what do I mean by reality-centric AI. Is AI which aims to solve real-world problems and which operates effectively and accountably given the unavoidable complexity that the real world entails. And also AI which is not marginalizing us, the humans, but rather empowering us. And as part of that research agenda, we also outline not only a motivation, but also a way forward in terms of what do we believe that this research agenda should entail. And one of the most important pillars of this agenda is what we call Pillar 2, which aims to build and create models and ecosystems associated with these models, which are able to operate with real-world data. And what do I mean by real-world data? Data that is either incomplete, at times may not be even available for the problem of interest, may be biased, may have errors or noise, may arrive with different types of delays, may be costly to acquire, may have privacy concerns if shared with researchers, and importantly, can change as circumstances change. These are just some of the many imperfections that come with real-world data, and this poses important challenges. And at this stage, we may wonder, well, how can we do that? How can we deal with this type of real-world issues? And I want to emphasize that this is true not only for medicine, but it is true for all the domains I mentioned before, from finance to smart cities, from economics to climate change. And some of the solutions that come to our mind when thinking about addressing these challenges are missing data imputation, which is not a very cool topic, but a very important one. So many people think, oh, why is missing data imputation important? Well, it's very important because often the data may come in an incomplete form or may be costly. Today, we are going to talk about data-centric AI. And like Fergus, I'm super excited because we have several panelists that have done amazing work in this area and are visionary in this area. So you will learn a lot from them and their way of thinking. And then in subsequent sessions, we would like to talk about related technologies such as synthetic data. And because the data is costly and complicated to acquire, active sensing and monitoring. But today we are going to talk about data-centric AI, so I'd like to give the floor now to Nabeel to talk in more detail about it. Thank you.
Okay, so good afternoon, everyone. So I'm super excited to be here to talk about data-centric AI. Broadly, what is data-centric AI? And then talk about some latest tools that we've developed in the lab from over the last few months or so. So as Mihaela mentioned, challenges in real data are obviously significantly abundant and obviously impactful for machine learning systems. And this becomes even more impactful when we start taking it to high-stakes domains like healthcare, where any issues in the data are going to affect our machine learning models. But the real people that really get harmed by this are the patients that are going to be impacted by these poor performing models as a result of the data. And we might find actually in reality that we have data which is mislabeled in a healthcare context. We have incorrect disease labels assigned to individuals. We might have mismeasurements of incorrect biomarkers being measured. We might have noisy data itself, both from measurement devices or coming through human beings. We might have errors propagating from system to system. And we might even, specific to the healthcare context and many areas of machine learning, have underrepresentation, where we have small minority subgroups in our data sets, or we might have long tail outcomes that we really actually want to still perform on quite well. And this makes operating machine learning on these challenging data sets quite an important problem. But it's not just confined to healthcare. It might be in an image data set. We might have huge amounts of images where we have such a blurry image like I show on the screen. How do we identify this such that it doesn't affect our classifier? Or we might have a text data set where we actually have a mislabeling of a clearly positive movie review that is negative. And solving this problem is fundamentally important from a data perspective if we want to get machine learning to work well in the real world. And the question is, how does machine learning currently handle this very real world issue of data? So the current approach to machine learning is largely what we call model-centric AI, where data is often considered a very fixed asset, where we do often one draw of a data set, we pull a data set from Kaggle, we have some image repository like ImageNet, which we're building models on, or we might do a query of a SQL database. But this is often considered like a once-off fixed asset, and now let's go to the machine learning on top of it. And then we go do a lot of model iteration, with it being a focus where we want to build new models, new architectures, loss functions, and optimizers. And of course, these are really fundamental problems in machine learning, and really great work is being done in this area. But we need to also focus on this other area of the data and how does it affect the model. And that's where data-centric AI comes in. We really want to bring data iteration in focus, and we want to build systematic tools to actually do this data iteration for machine learning. We want to build systematic tools as a data-centric AI community for data acquisition, cleaning, auditing of data sets, and even generation of data sets. And of course, then we have the model where we'll have new developments of standardized architectures, from neural networks to boosting transformers, etc. So data-centric AI really tries to focus in and hone in on this data aspect and get it right. And to give an anchoring definition for everyone in this session, we think that data-centric AI encompasses methods and tools to systematically characterize data sets, evaluate, and generate the underlying data used to both train and evaluate machine learning models. In today's session, we will primarily focus on this characterization aspect, but we will be talking about other aspects, for example, generation, where we talk synthetic data in the next inspiration exchange. So data-centric AI, of course, is super, super important. The big challenge that we fundamentally face as a community right now, it's quite hard to engage with. At the moment, we don't have fully standardized processes. Practitioners who want to bring data-centric AI in don't have some guide to necessary considerations across the entire pipeline. And we have no common place to really bring tooling or opportunities for researchers to tackle in this space. So one thing that we've introduced in the lab a bit of time ago now is something called DC Check, together with Fergus and Mihaela, which is a data-centric AI checklist, basically to guide the development of end-to-end machine learning pipelines. And the goal of this checklist is really to elicit data-centric considerations across the entire ML pipeline, all the way from data, training, deployment, and testing, but really to get people really to think about what considerations might they have from a data perspective at the various stages of the modeling pipeline. We encourage you to take a look at the lab's website for more on this, or our previous inspiration exchange where we delved into DC Check in more depth. But today's session will really focus on this idea of data quality evaluation, which I highlight there. And for this year, it's this area of data characterization. It's how can we build systematic methods to curate data sets in the first place? So we all know that auditing and curating data sets at scale is absolutely hard. It's very time consuming. And the big issue, it involves a lot of human effort to curating data sets in the first place. And what we're really trying to do in this research agenda of data characterization across the machine learning community is how can we enable humans to do this in a much easier method by actually automating some of the process, not cutting the human out, but rather how can we surface interesting examples such that humans know what to actually audit in the first place, rather than having to audit millions and millions of examples in a data set. So this idea of data characterization really thinks about this idea that not all data points in some data set are equal to one another. And on this basis, we aim to assign a score to every individual sample within a data set. And we aim to use these scores to really understand which samples are hard, ambiguous, or mislabeled. So this would be challenging for a machine learning model, but also which samples are actually quite learnable and important for the model to actually learn on. And that's what this area of data characterization really tries to fundamentally address. So you might say, what are some applications? What can I do with data characterization before showing some methods? So imagine I want to audit an image dataset. I have millions of examples, for example, in Celeb A. We might find that easy examples surfaced by a data characterization method are ones that you can see on the screen, and are clearly examples we might want to train our machine learning model on. We might then surface some ambiguous examples, which really call for us to really think and scrutinize our data sets and really think, do we want to bake these biases into our models in the first place? For example, a characterization method might find that ambiguous images are those of females with shorter hair. But we might say, this is not a bias we want to build into our machine learning models, but what a data characterization method has done is it surfaced this issue to a practitioner such that they can actually rectify it before baking this bias into their model. We might have images which are also blurry, which we might then want to do a different action and get rid of them, or we might have obscured images as well. And finally, a data characterization method might surface hard examples where we actually find these examples are just fundamentally mislabeled and we want to go fix them. So we can see what data characterization could actually be used for. And there's a wide variety of methods across the literature, including Dataiku from our own group, which was at NeurIPS 2022 last year. But as you can see on the screen, there's a huge amount of methods which have been developed in the community and really target this problem quite well. The issue is that all of the methods you can see on the screen have really focused on the classification problem. And of course, this is very important, but what it really does is it neglects the fundamental and very important area of regression. Regression is very crucial in many areas and many sectors in society, and especially when we think about the healthcare scenario. Regression is very important when we want to do sorts of predictions like length of stay prediction for somebody in an ICU. In prostate cancer, we might want to predict continuous biomarkers of patients. But in order to do all of this, we also want to assess the regression datasets before building these very, very important and high stakes regression models. The trouble is, current classification methods simply just cannot be applied. And the reason for this is many of the ones I showed on the previous screen actually operate on the discrete outputs or softmax outputs of classification models, which we just don't have access to in the regression setting. So this calls for new methods to how can we do regression with data characterization. And for this year, we introduced triage, which is a method for characterizing and auditing training data for improved regression. And this was joint work with Jonathan Krabbe, Xiaoxi Chen, and Mihaela Vandesha. And this paper is to be appearing at NeurIPS 2023, and the paper and code will be coming soon. So the major challenge we find for regression is that we really just need a principled scoring metric to do this in the first place. And what in triage we do is we say the full information of any uncertain label lies in its probability distribution. And if we have this probability distribution, we then can compute any probability of a variety of outcomes. The question is, how do you do this for regression? So we aim to address the limitations first of point estimators. So a point estimate regressor, we simply obviously cannot do this, and we have no notion of uncertainty. We might then have the second level, which is an interval regressor, which gives us a predictive interval, or some might even now know things like conformal intervals. However, these also do not give us the full probability distribution and don't allow us to compute these probabilities of various outcomes. Of course, Bayesian methods do offer us this notion of having this probability distribution. But what is the major drawback of Bayesian methods is A, we require setting quite good priors on our methods, but additionally, it requires us actually using a Bayesian method. We might have to be forced to use a Gaussian process regressor in order to do this. What we actually desire is to have flexibility to use any regressor for data characterization in a regression outcome and give a practitioner flexibility to use the regressor of their choice. So that's where we introduce triage. So what triage does, it computes a pipeline approach where we first compute something called the triage score. We analyze these triage scores with something called training dynamics, which I'll get into on the next slide. And on the basis of these training dynamics, which actually tell you how these scores evolve through the model's training, we can then characterize samples as likely overestimated, well estimated, and underestimated, which we can then use for downstream tasks. So the first thing to start with is conformal predictive distributions. So for those of you who don't know, conformal prediction as a broad area aims to is actually quite powerful. It provides model agnostic and distribution-free assumptions, but something to highlight of conformal predictive distributions versus the conformal prediction you might be thinking of producing intervals is that we are actually able to produce a full distribution for our outcome. And how do we actually do this? So in the paper, we delve into this much more. Just to give a high level, by correct choice of non-conformity score within conformal prediction itself, we are able to sort our non-conformity scores in such a way that they're able to satisfy the exact properties of an actual predictive distribution itself. Once we're able to satisfy the actual properties of a predictive distribution, we can then assume this is the same thing or interpret it in the same way as a probability distribution. And what this really allows us then to compute is what we're really after is the score, the probability of that some given y is less than our predicted f of x, which we take as our triage score. What we do interestingly then in triage is rather than doing it at the end of model training, we actually compute the change of this probability through the model's training procedure. And why is this interesting? Because we actually see in the picture you see on the screen, some samples actually converge quite quickly, and this probability score gets quite stable, quite fast. Some samples actually oscillate around quite a lot. And this actually gives us quite a bit more information than just doing it right at the end, because we're able to disentangle samples that were learned a lot slower versus samples that are learned quite fast by our model. And on the basis of this here, as you can see on the top, we're able to then identify samples which are underestimated, overestimated, or well estimated. And then what we do is we compute, as you can see in the middle of the screen, the average confidence of the score as it progresses through training, as well as its variability. On the basis of this, we then can take these scores and use it for downstream tasks or to sculpt a data set. But let's take a concrete example in healthcare to show you what it can really do. So we show that triage can help, for example, length of stay prediction in an ICU to really get that prediction much better. We show improved downstream performance compared to residual baseline, which is commonly used in the literature. But what's specifically interesting about this result is we can see we're able to even use much less data and yet achieve the same performance, which is actually interesting both from a computational but also from a collection perspective, that actually sometimes less data is more if we're getting the right data in the first place. But in healthcare, we also want to go beyond average. As I showed you on the screen, we have better overall regressive performance on average. It's not shown here, but you can more than likely go look in the paper itself. We show significant performance benefits for the tails of the distribution. So these are small subgroups of patients as well as long tail outcomes. We show that we actually don't sculpt these individuals out of the data set, but rather by sculpting our head of the distribution, we actually tilt our regressor to the better and true manifold and actually then have better performance even on these smaller subgroups compared to previous methods. We then finally do one assessment where we say, can triage help you cross-setting if you want to deploy regressors across countries? So let's imagine that right now I'm in the UK and we have a small data set of patients in something called the Q-Track data set. These patients might be insufficient for us to train a really good regressor, but we want to do prostate cancer prediction of PSA scores in the UK, but I just don't have enough data. Could I actually sculpt a larger data set, which comes from another country, but is actually just fundamentally different and has some sort of distribution shift? For example, the SEER data set coming from the United States. And we say that, yes, we can. We show that we can use a very small data set coming from the UK as our calibration set to aid the sculpting of our much larger data set. And this allows us to actually transfer a lot better when we bring this regressor back to the United Kingdom on our small amount of data, which shows that we can really even use ideas of data sculpting to go beyond just IID performance in different settings. And what's very interesting is that we only require very few samples from the target domain, even as low as 10 and 20 samples from the target domain, just simply because we're calibrating on that. And we show that this actually performs much better than other sculpting-based approaches. But additionally, if we were to just combine data sets or do transfer or fine-tuning on the smaller target data set. But what else might you want to know about triage? We show that triage can be used for consistent characterization. One interesting thing, the property is that for similar performing models, we get consistent characterization. We also show utility for both feature acquisition and dataset selection, but also versatility across a variety of downstream models. So if all of this has really piqued your interest, both data characterization for classification and data characterization for regression, you might be asking, how can I apply data characterization to my own data and really bring these benefits to my own problems in my own domains? And for this year, we're super excited to introduce a new package called Datagnosis, which is really to bring data characterization to your own data. We provide a unified API and interface for this open source project with currently 12 state-of-the-art methods implemented with an easily extendable plugin style interface. And we're super excited for the community to engage with this package, try it on their own problems, and even contribute methods to this package, such that we can really bring this area of data characterization to the fore and really address problems in the real world. I now hand over to Rob to talk to you a bit more about Datagnosis.
Excited for data characterization methods, and now I can show you Datagnosis and how you can apply it to your own data. So hello everyone, I'm Rob Davis, I'm a research engineer with the Centre, and yeah, let's have a look at Datagnosis. So this here is the GitHub page. So we're at Schaar Lab /Datagnosis, and you can see we've got basic information about how to install the library and some sample usage. Quickly, I'll just show you here in the table below in the region, we have all of the different state-of-the-art methods all laid out for you with a brief description of what each score is all about, what each method is all about, how they calculate the scores and what the scores mean, and then links to all of the papers. So hopefully that gets you straight into understanding and using the methods as quickly as possible. I will say that it's released on Pipey, so it's as easy as it could be to install, just with a pip install, and it's fully documented on Redux. So you can see everything from our data handling classes to our plugins, everything is all available for you to read online. I'm going to just run through quickly one tutorial that we have for a simple toy data set. Before I hand back, so you can see it in action. So I've run all the cells here beforehand, so just for the ease of the demo, but all of this you can see, all of the cells running very quickly, so you could be very excited. It was super quick to run. First of all, yeah, as I said, pip install Datagnosis sets up installs the library in your machine, sets up the environment. That's what you use to do on Colab. All of these all the tutorials we have for Datagnosis are available from the GitHub website, so you can run these yourself as well. But yeah, if you're on Colab running the tutorial like that, all you do is pip install, and then you can see in the next cell we set our level of logging, so we can have no logs, info level logs, debug logs, whatever you like. We're going to be looking at the info level logging that's built into Datagnosis. The data set we're using here, as Nabeel said, you can use this with any data set. We want you to use it on your data, but in this case, with the toy data set, the iris data set. So you can see we've got our 4 feature columns here and our target column. In the next cell, all we do is some very, very quick pre-processing of the data, some standard scaling. We do our test train splits. And then the important step in this cell is creating the data handler object. So that's the data handler that comes with Datagnosis. All you need to do is pass your training data that you will be using to fit your hardness characterization method with, and you pass those in the form of either a pandas data frame or numpy array. So we're using very, very commonly used types here. The next cell we're looking at the classifier that you're using. So Datagnosis at the moment is all about classification, using classification, and yeah, in this case we're just looking at a simple multi-layer perceptron. So again, you could be using any PyTorch model you like. It is limited to PyTorch at the moment because that's inherent to a few of the different methods that we have included. But within that, you could be using any architecture you like. And you see, we just selecting a few different values for our parameters for our model there. Here's where we get interesting in our plugins. So each of the methods is introduced as a plugin, and we can see all of the different methods we have available with the plugins.list. And there you go, you can see we've got the 12 different methods available there. And we create our HCM, our hardness characterization method, with plugins.get. And then all we need to do is pass the name of the plugin we're choosing, so AUM in this case, and then some simple the model and the criteria and accept the simple information that the HCM needs to in order to initialize that object. Next, we fit the HCM, and all we need to pass to that is our data handler that we created earlier. And when we fit, we can see the loss reducing in the info level of the logs there, so you can see it's fitting nicely. We've got a couple of utility methods here. So a score description we can call on our HCM, and that prints out a nice little paragraph all about what the score is about if you need a quick refresher or you're just playing around with the code live. Just useful to have that there. You can remind yourself what these scores mean because each of the methods provide a different score. Some of them will be between 0 and 1, some of them are based on other factors. So we've got that explanation there for you at the tip of your fingers. And we can just see once we fit the scores, we're straight away able to print out the scores as well. So those are the scores we have calculated for our training set. And we can then plot the scores with HCM.plot scores, and we can see our distribution. And finally, we can extract our data points from the data set based on those scores. So with the function here, extract data points, and the method top m with n set to 10, we're extracting our 10 hardest data points. And then I just put it in a nice data frame just to view in the notebook here. We see the indices of each data point from the original data object that we passed into the HCM method. And we see the scores that is been calculated with each values and there. So those are like hardest to classify data points. If you've got time, I'd really encourage you to have a look at the other tutorials we have on the GitHub. There's one about an image data set and one with a more real data sets. That's the COVID-19 Brazil data sets. So you can try it out for yourself on a real data set before you try it out on your own. So that's it from me, other than to say thank you very much to listening to Datagnosis. Here's the QR code for the GitHub page, and we'd love to see you getting involved in the project. If you create your own plugin, as Nabeel said, it's very easy to do, then I'd love to see a PR on there and issues reported on the page as well. It would be really great to see. I'll see you in the comments and the issues on GitHub. Thank you very much.
I'd like to now move on to our panel discussion and introduce our 3 fantastic panelists. So our first panelist is Louise Ola, who is the head of machine learning at Photon. We're also joined by Dr. Manil Maskay, who is a senior research scientist in the Office of the Chief Science Data Officer in the Science Mission Directorate at NASA. And finally, we're joined by Dr. Peter Matson, who is the president of the ML Commons Association, as well as being a senior star scientist at Google. So I want to kick off the panel discussion by asking each of our panelists to say a few words about what they and their companies are currently working on and what they're interested in, and really with a focus on perhaps how the topic of data-centric AI either already does or can maybe play a role in this. So I don't know, Louise, if maybe you want to kick us off with this?
Sure. Yeah, thanks so much for inviting us. Very nice group you built up here. I am not familiar with the format yet, but it's impressive to see. And I mean, I'm familiar with Nabeel's work with the DC check and Mihaela's many ventures in the space, but I really like the format. But for the topic of today, I think a couple of us, we already worked together. That's why we are here today as a batch. So me personally, I lead the machine learning and AI work at Dot-Photon. We are a Swiss company that works on compression and optimization of optical data. But I don't want to kind of make this into a marketing event, and maybe talk just two sentences a bit more on the research side and the community building, where I think especially Peter, he is the kind of one of the people behind the scenes pulling a lot of the strings. We are trying to, with many people, build a community around this topic, and Mihaela is a big figure in that, you guys with your lab. And we had a nice workshop at ICML this year around this topic, where a new journal is also part of that activity, and there is some software development similar to the nice library that you just showed. And I hope we can maybe gather some momentum here today and give people some coordinates where they can contribute if they're interested in the space. There's new workshops coming up, I think, or in preparation for iClear, and the goal really is to be present at all the big venues and kind of evangelize for this type of work. So maybe I hand it over to Manil at this point.
Yeah, thank you, Louis. I'm Manil Maske. I'm really happy to be here. I wasn't sure if I was going to be here until last night, but happy to join. And then I echo Louis. This is a fantastic, I think, venue, and the amount of enthusiasm and people participating is great. A little bit of background on where I come from. I am a computer scientist, even though I work for NASA. I work on the Science Mission Directorate. We have 5 different divisions within science: Earth science, astrophysics, planetary, biological and physical science, and I'm missing one. Did I already say astrophysics? But well, there are 5 of them, right? So the way our charter is to answer questions, right? Scientific questions. And to do that, we launch missions, right? You've probably heard of James Webb Space Telescope, right? That's one of the missions. The idea there is you have a hypothesis, and you try to answer that question by collecting data. So you see the emphasis on data, right? We've been collecting data for a long time now. I'm most familiar with Earth science, which has about 82 petabytes of data, and soon it will be around 250 petabytes because of the larger missions coming up. So we use that data to answer these questions, right? And AI has been a big part of it for the last 7 or 8 years in answering those questions. But we have a problem with managing that data for AI. We have a big problem, right? If you think about science, things that we want to understand happens very rarely, right? But we also have this large amount of data where things is basically needle in a haystack problem, right? So how do you manage that data for science is a big problem. I do resonate with what Mihaela said about real world, right? A lot of the advances in the AI you see in prestigious journal is about accuracy, right? Which is great, but for science, I think we care more about shortcomings of these algorithms. We want to understand, right? I've worked with the domain experts, and when I go and present these AI outputs, understandably, they're hesitant to accept why it is doing better in some cases than what their physical models are doing. So you need we need a mechanism, a data-driven mechanism, to show them why is it the case, and make them understand what the model is doing. So that ties in with the reality. Wherever we start out in a new AI venture, we always have these use cases and applications in mind, right? And we showcase the power of AI using those. Finally, I do want to say that we want to be in a state where we can learn from these AI experiments and probably generate new hypotheses, which is going to be a big game changer in terms of doing science. So I'll just leave it at that. Peter?
Thanks, Manil. So I'm primarily here today with my ML Commons hat on. ML Commons has a mission to make ML better for everyone by building out the ML ecosystem. And we see that as having three key pillars: benchmarks for everything from speed to quality to safety, data sets, both evaluative and training data sets, and the best practices sort of guide everyone in using those data sets, using the models we're developing in a responsible and effective way. In terms of thinking about data-centric AI, I'm really guided by the phrase, data is the new code. I think there's a real mindset shift that we need as a community in terms of how we think about data. Data is what determines the behavior of an AI system. You don't program an AI system with Python, you program it with data. And this is a very different way of thinking. And there's some important rules that I think fall out from that realization that are things we as a community need to start thinking about. One of those is that data is mutable. So in science, we have a data is immutable mindset by default. We got our data, now we're going to do some analysis and figure out something interesting. But for AI, you're trying to create a system that does something in many cases. And with that mindset, you want to collect some data and then possibly go collect more data, or refine the labeling of the data, or eliminate some data that's leading to incorrect outcomes. The data is something that you actively engineer. Another important rule that comes from this mindset shift is that the single most important data set you have is your test data set. From early AI, we've been trained to pull it out of our training data set, identical distribution, and then we could use that to show how clever we were in making a model. But the reality is, when you're trying to solve a problem, you want your test data set to reflect the problem as accurately and with great difficulty as you can. This is how you will know whether or not you've actually got the training data you need and how you can guide that refinement process. One of the interesting projects, because I know this is to some extent a healthcare related audience, that ML Commons is working on is something called MedPerf, where we help people build distributed medical test sets. So you want to test a medical AI application and not have it fall down as soon as it applies to a patient that wasn't represented in the training set. You really need data from a lot of different clinics and patients. And one way to sort of accumulate that is with a distributed federated approach. The last thing I think we really ought to be thinking about actively as a community is that if data is code, we're going to need a whole tool stack for working with it. Think about everything you have for programming. You have debuggers, you have profilers, you have IDEs, you have GitHub. The list goes on. And we're going to need to build all of that for data, for this sort of mutable, test-driven notion of data. And that's something we're working really hard on at ML Commons with some fantastic folks, including Lewis and Manil. In particular, we started working on a format we call Croissant, along with folks from places like Hugging Face and Kaggle, to try and have a common top-level metadata description of data sets so that we can build standardized tooling for working with them. Right now, every data set is its own beautiful pearl, and we need to get to the point where it's similar to a program, and that you can point a debugger at or a profiler at a variety of different programs. So those are some of our thoughts and things we're trying to work on to help build out the data ecosystem.
Thank you so much for those answers. Mihaela, I know you had some questions for our panelists.
I think Nabeel had first, so I should let Nabeel ask the questions, not me. I have many questions, and I'm very intrigued by what all the three of them have said, but I can jump.
Nabeel, take us away.
So I think all three of you have mentioned like super interesting things about things that maybe we need to be doing in the future for future research. I'd be curious actually to get all of your opinions of how would you say all of these changes of either both problems we focus on, like as Manil mentioned, I guess on like science type of problems, and how would different data modalities really factor into this, both from like text, images, tabular being very, very different, being very like heterogeneous? How does that like impact the future development, I think, of data-centric AI? Because I guess at the moment we do try make it like very modality agnostic to try be fit for purpose for everything. And do you think there is this focus, or like where we should be a bit laser focused on a data set and its nuances?
Maybe I can start. I did a little bit of unscientific experiment before I came here. I looked into data-centric AI in terms of adoption across mainstream versus science, and I didn't find anything within science. Very few. Whereas in mainstream data-centric literature, there's quite a lot of papers being published in the last few years. And this, I recently made a presentation at Croissant workshop too, meeting as well. And it was obvious when we're talking about science, and especially the types of science that NASA does, that it's not everywhere. I think medical is a little different. The nature of the data itself provides a lot of complications, right? We build advanced sensors, right, where while you're observing for space and time at one location is not the same the next day, right? The scale of the things that we do is not similar, right? Temporally and spatially. For example, I can give you an example of maybe an event, right? There's a storm event that can happen for half an hour, right? Storm event that can last for weeks, right? Same thing with the spatial nature too, right? If you have a hurricane, it can go from Atlantic to Pacific, right? That's a big geospatial area. Some of these things are very domain specific things, which are hard to capture in more generalist way.
If you allow me, Fergus, now I jump and ask a question, one to Luis and one to Peter, if that's okay, unless they want to answer this particular question. So Luis, to you, just brief answer. There are many students in these calls, in these sessions. Where do you advise them to look for papers in data-centric AI? And where do you advise them to publish papers on data-centric AI?
Well, this is such a coincidence. I just put the two perfect links as answer in the chat. So I think one would be obviously the workshop that we launched, where Mihaela also and many other great speakers presented their vision. So that will be continuing. It's called DMLR. As I said, the links are in the chat. And just now, we also launched a new journal under the JMLR umbrella, which is focused on data-centric work. And the link is also there. The open review is just ready and for submissions. And the goal really is to, I mean, we also need people to contribute as reviewers and editors. But if you want to have high impact work in the space of data-centric machine learning, we really want to build this as the prime venue for our community. So everybody go have a look and send your best work and become a reviewer, and obviously come to the workshops or help organize them. I think Manil is also very much involved in that, and there is a Discord. So it's very low, so there is no hierarchies or big fuss. Just come along, and this is very open. So yeah, I invite you to check that out.
Fantastic, Luis. Peter, I have a question to you. You are doing all sorts of amazing things within ML Commons. And do you have a suggestion to people that are building open source packages related to data-centric AI? As you see, we are building some, and I'm sure other labs are as well. How do you see that we can come together as a machine learning community interested in data-centric AI to connect these efforts, to connect these open source packages, to build something bigger and better together?
So I give two answers to that. One answer is around standards and extensible frameworks. I think in particular, standards like Croissant are the vital foundation to doing this sort of thing, because it encourages people to take one easy step for their data set that unlocks all of the functionality we're all trying to build in a much easier way. And so we're very excited to see things like that appearing on the major portals, especially, so that it's easy to get for our data sets. The second answer is around, it's similar to the venues. We need to have a consistent set of venues. And I think we've taken the first step with the workshop, but I would like to see us have tracks so that you know it will always be there at, for instance, ICLR, ICML, and NeurIPS, which to some extent we already do with the datasets and benchmarks track. But part of that is also getting the mindset shift from, I built a data set, look, I published it in story, to thinking about how do we build better data sets? How do we improve core existing data sets? How do we develop algorithmic or theoretical techniques for working with data sets? And then those venues become good places to promote and talk about the kinds of tools that you're describing. So standards and frameworks to bring them all together, and ML Commons is very active in that with Croissant, and we are working on a data framework. And then you need a place to promote, talk about them, and exchange ideas. And starting with workshops and a journal and then building up to tracks very quickly, I think is absolutely essential for the field.
Thank you very much, Peter, Luis, and Mihaela. If you allow me, Fergus, a shameless advertisement that together with Isabelle Guillon, Nabeel and I are planning to give a tutorial at the NeoRIPS 2023 on this data-centric agenda. So not for the panelists who are experts in this area, but for the junior people on the session. If you are coming to NeoRIPS, join Isabelle, Nabeel, and me to learn more about data-centric AI. And we will make sure, Luis, Peter, and Mihaela, to highlight what you said here and present that as part of the tutorial as well. Thank you.
Fantastic.
Thanks, Mihaela. And thanks once again, Peter, Luis, and Mihaela. I want to take a few questions maybe from the audience now. I see a lot in the Slack, so I want to make sure we've got enough time for that in what remains. If you could just, when called upon, unmute yourself and ask your question if you're able to. If you're not, I can read out the questions instead. I think the first is phrased as a comment from Anna, but I actually think it's a really interesting maybe topic to discuss more generally. Anna, I don't know if you want to unmute and make your comment/question.
Yeah, hi everyone. And I'm a data scientist at the Medical Affairs in Novartis. And throughout my previous experience, I found that a lot of the times, as a data scientist, I would have no idea whether a code is overrepresented in a data set, and later to find out that actually this is kind of artificial because it's a reimbursement code, right? And so that was an issue we were facing quite a bit, which is quite sensitive. You know, what do you do? You have to shift your analysis plan effectively. Yeah, so I was wondering, as a comment on that, I think this will effectively be made more transparent as the NHS opens up through the SDs that they're building. But yeah, I was just referencing that with respect to the mislabeling that can happen in real world data. Thank you.
Shall I say something about that, Fergus? If you
Yeah,
allow
sure.
me
I think
to?
that's good. Yeah.
So Anna, I think that this is a great point you are making. There is two types, of course, of mislabeling, and it's not only labels. You are especially right about the labels, but labels or even features at times. I think there are noisy and there is error that's not malicious, if you like, or due to bias. It's just because somebody didn't pay attention. That's relatively easy to deal with. What's a lot more interesting is exactly the point you are making. What happens if there are biases of all sorts, inclusively strategic annotation, because somebody may have a certain incentive to mislabel a sample because of financial benefits. I think that this is a very interesting area where the world of fairness, causal inference, and data-centric need to join forces to look at these examples such that they don't propagate in subsequent data sets. And the only thing I'm going to say is I'm going to invite you and everybody interested in this topic to join us next time when we are going to talk much more about synthetic data and how synthetic data can deal with some of these biases, and whether that's, I would be intrigued to find whether you think that this is a way of thinking about that. I don't know whether the panelists have anything else to add.
Maybe just a note on like to do some science fiction and like an answer at the same time. So I would even go like if we go 20 years ahead or 30 and talk about crazy ideas, I think we can even push this notion that Peter mentioned further and like ask ourselves if we can do away with this model and data distinction that we now have for historic reasons, right? Like we had all those nice TensorFlow and PyTorch frameworks being primarily developed, and they've grown and blossomed and become also somewhat like convoluted in some ways. And there is some, I think, very exciting projects, both in the commercial domain or by startups or open source, that kind of wonder if we can do away with like this distinction also on the infrastructure level, right? We saw this nice library that you guys are working on in the lab. And I think that is a huge opportunity actually, because if we, I mean, at the end of the day, right, the model parameters, it's just a different representation of the data. It's just a transformation on data. That's what it is. Like a machine learning algorithm is an iterative application of a transformation to the data to get a different representation. It's not so much different from other kind of processing pipelines that might happen before it. So this distinction where we say, okay, now this is an input and now this is the model, it becomes more and more artificial, I think, the closer we look at it. And if we then kind of mirror this back to what does this mean for infrastructure, for the tooling that Peter mentioned, I think then we should start thinking about like a vision for coherent, lazy, scalable tooling where we basically, I don't know, you just park everything on some S3, you can share it easily via a link, whether it's a data set or model weights in the classical sense, it's just a flag in the metadata. And I think this is the kind of stuff that is really interesting and also then helps to get back to your question, I think, with these traceability problems. Because if we have this kind of end-to-end view and we know, okay, where does our observation stop? I mean, there will always be limits. We will not have complete surveillance. Otherwise, this is a different kind of nightmare that we, then live in. But I think that we are aware of like known unknowns, basically, right? And can kind of trace this. I think this is tightly knit together with this infrastructure problem, because as long as we have too many, ML ops tools scattered all over the place, this is harder to achieve. And this would be my bit long-winded answer.
But I think it's very exciting, Luis, because the reality is, in this reality-centric agenda that we put forward, we kind of say as one of the pillars, what about a future where the machine learning model is actually going to deal with any data that is thrown at? and be able to internally to do all this processing and debiasing and denoising and everything else, rather than the separation. So I think we are agreeing with you, Peter and Manil, that indeed this division seems artificial, and cleaning the data first to give it to the model doesn't seem the right choice, but rather more this indeed continuum where, yeah, I would agree actually.
Thanks for the question, Anna, and thanks, Mihaela and Louise, for the responses. The next question I'd like to take is from Andrew Boardman for Nabeel. If you want to unmute yourself and ask your question.
Hi, so this is a bit more, I guess this is a bit more specific about the presentation, but I wanted to ask, you showed the interesting result that over the epochs of your model training, that your instance hardnesses would tend to either go up or down, depending on various qualitative aspects, well, various aspects of the example. I wanted to ask whether you observed similar effects and similar relative instance hardnesses if you chose, say, higher capacity models that were better able to model the data, because I guess my intuition is in the limit of a model that really doesn't work at all and has no ability to model the data, you don't observe any differences in instance hardnesses between different examples. So I guess to put this in a more prosaic way, more poetic way for the panelists, I wondered if you could get better data-centric AI somehow by increases in the capacity and the ability of your models.
Thanks so much, Andrew. So that was actually something that at least it bugged us quite a fair bit during this project. And one thing that we ended up doing in almost like an ablation study was kind of trying to figure out this exact point. So if a model is, let's say your regressor was actually just really poor capacity and you had quite a high capacity one, of course, so we found that there would be a fair bit of differences. What we did find interestingly, though, if we had multiple architectures or even slightly different parameterizations of models, but they overall converge to relatively similar levels of performance. At that point there, if they converge to similar levels of performance, at that point, actually the scores are fairly really well correlated across models. So in terms of like the scores being fairly similar across these different models. So there definitely is this like model dependent aspect to it. But at least if the architectures are different, but you're kind of converging to similar levels of performance, at least you can expect stability around that.
That makes sense, and that's really encouraging. Thanks for the great presentation. It's been really interesting.
Thanks for your question, Andrew, and thanks, Nabeel, for answering it. I'm afraid we won't have any time to take any more questions live, but what we'll do is, because all the questions are in Slack, is I'll invite Nabeel and any of our panelists if they're willing or able, but certainly Nabeel and Rob from our lab to maybe go through the questions and provide some answers to some other questions which we didn't have time to cover. I'd just like to wrap up by highlighting our next couple of sessions. And so Mihaela's presentation, she spoke about these kind of like some of these four main problem areas for this kind of pillar 2. And so today we discussed data-centric AI. Our next session, as Mihaela mentioned, is going to be on synthetic data, and this is going to take place on November the 6th. And then on December the 4th, we're going to have more of a session around kind of active learning, active sensing, and monitoring. With that, I'd like to just thank once again our 3 speakers from our lab, as well as our 3 panelists for joining us today. And thank you all for joining us. Please do encourage any friends you might have who might be interested in these sessions to either check this session out when it will be put on YouTube soon, or indeed signing up to receive notifications about future sessions. And with that, I'd like to close the session and look forward to seeing many of you on the 6th of November for our next session. Thank you very much for joining.